All right, so welcome back to these computing sessions. Um, in this afternoon part, we will write small computer programs. Um, and to do that, I'm going to share my screen. All right. So we'll start with some simpler hands-on activities, then have a 15-minute break, and then we'll have some more hands-on activities and some time for questions. So we are going to talk about something that we have already addressed this morning, which is the importance of lists or sequences and transformations of those lists or sequences. And with lists and functions over lists, we can do really a lot of stuff, like Professor Zenano said. And you may not have noticed, but we have been implicitly working with lists. When we were talking about a binary code, we were talking about a list or sequence of zeros and ones. And we know since we were little that a word is a list of letters. For example, the word cat is the list of the letters C, A, and T. We also know that a queue is a list of people, and so on. So lists, this ordered data structure, is very useful to model real life aspects. And it's one of the most important, or even the most important data structure. And lists allow us to represent elements in an orderly manner. So, for instance, the lists 5143 and 5134 are different because the positions of the numbers 3 and 4 are different. In the first list, 4 appears before 3, and in the second one, it appears after 3. So the lists are different even though they have the same numbers. Both lists have numbers 1, 3, 4, and 5, but they are distinct because the position the position of the numbers in the sequence is relevant, is important. And these two first lists are also different from 51134 because number 1 appears twice in the last list, but only appears once in the other lists. So in a list, we care about the order of the elements and we care about the number of times each element appears. Lists aren't just sets, they have an order, okay? And how do we represent a list in Haskell? Well, for instance, say that I have the list 1, 1, 2, 3, 5, and 8. So the list which consists of these numbers. To start writing a list, we use these parentheses. And to finish, we use another parentheses. I think that's how you say it.
Yes.
And so this is like a way to tell the computer, hey, the list is gonna start here and it's gonna end here. It knows where to start reading the list and where to stop reading the list. And then we separate the elements by commas, okay? So the computer must know that you want to write 2 1s and not 11, okay? So we must have a way to separate the elements, and for that we use commas. So we have a very simple exercise for you, and I will ask Luis to put in the chat a link that I will ask you to click on. And
Yeah,
okay,
it will
so I think
give
I
you
stopped
access to a
sharing.
binder that will open Jupyter notebooks. with some exercises there.
Yeah, and please let us know when it has opened, because it may take some time. So when it has, once it's loaded, please let us know.
Just because he's executing and preparing the environment in order for you to execute cells.
I'm there.
Yeah, you are there. You are there as well? Okay, perfect.
Okay. So you can see this we have lots of fun for you today, and this is basically a what we call a Jupyter notebook, and this is what we use in our classes when the kids go to the computers, because we can have text and images, and we can also have cells with code that we can sort of run the cells locally. So it's a very friendly environment. That's at least what we hope. So the first thing we want you to do is to execute this first cell. And you can do that by clicking here on the play button, or by pressing the Shift and Enter keys. But yeah, if you just click here.
You need to put the cursor there and then click on the play button or Shift Enter, okay? So by doing that, you will execute the contents of that cell. So, and as you can see, there are just a few instructions there that will allow you to upload specific things that will be needed for the rest of the exercises.
Yeah, and once you run a cell, you should see either a symbol or a number. Either a symbol or a number. So for instance, this cell has this symbol here because I executed it. This cell has no symbol because I didn't execute it. Okay?
Yeah, so it will not happen anything, okay, except that one. Okay, that's perfect.
Yeah.
It says, yeah, the star or number
Or a
says
number.
that that cell has been executed.
So you just need to click the cell and click here on the play button.
Just honoring the cell, no?
Yeah. Once you see the symbol, that's okay, and you don't need to know to do anything else.
Yes.
Then you should see the.
If there is any problem, we will see in the next cell.
Okay.
If there is something missing, so no problem at all.
Okay, so we will first talk about numeric lists, that is lists whose elements are numbers, and we will start with a very famous sequence called the Fibonacci sequence, and this is a sequence that is built in a special way. So the sequence starts with 1. Then we have another one. So the first two terms of the sequence are 1, 1. And then we get the other numbers by adding the first two numbers. So for instance, 1 plus 1 is 2. So we have a 2 here. And then 1 plus 2 is 3. So we have a 3 here. And then 2 plus 3 is 5. So 5 appears here. And then we have 3 plus 5, which is 8. So 8 appears here. So this is just for you to practice how we represent lists here on the computer in this in the Haskell programming language. So we are just asking you to write the list of the first 8 numbers in this sequence, okay? So we need to start the sequence with this symbol, left bracket. And then you need to start writing the terms separated by commas. So the terms that are there, which are the first 6 terms, are 1, 1, 2, 3, 5, 8. And now you need to compute 2 more, okay? So you just need to sum 5 and 8, and then sum 8 and the thing that you get. So you just need to sum the 2 numbers that appear before. So can somebody tell me what comes after 8? 13, exactly. And what comes after 13? 21.
Yeah.
Yeah, perfect. Because that 21 is 8 plus 13. So that's 21. Okay. And we finish with the right bracket. And I may execute this cell or not. It's a bit irrelevant. If you execute it, it will just say the thing that you wrote because you're not asking it to do anything. You're just saying, okay, this is the sequence, and you will answer you with the sequence.
But what it is saying implicitly is that, okay, I accept this,
Yeah.
okay, and so this for me makes sense. So it's a sentence that I recognize as a right sentence, okay?
Yeah, and this next this B exercise is very simple for you just to practice writing the sequence. So we want to write the list of the first 8 numbers in this sequence, but in descending order. So starting from the largest number and ending up in the smaller number. So we start with 21, and then we have 13, and then 8, and then 5, and then 3, and then 2, and then 1, and then 1. Okay, so I just wrote the sequence in descending order or backwards. And doing this by hand is a little boring. So later on, we are going to see a transformation that automatically writes a list in reverse order, and we will also see how to write a sequence in descending order. Okay, now I'm going to share another window. We will go back to the PowerPoint. Okay. Suppose that Okay, so suppose that we want to compute the sum of all those 8 numbers in the list. Okay, how do we do that? Of course, we could just write 1 plus 1 plus 2 plus 3 plus 5, etc. That would work. But there is a function or transformation called sum that allows us to compute the sum of all numbers in a list. So how do we do that? We start by we start by writing the list, and then we sort of write something that visually looks like an arrow. Okay, so it's a vertical bar and the greater than symbol. Okay, and it kind of looks like an arrow, and then you write the transformation afterwards. So you have the data, the object, the thing that you want to transform, and then you kind of shoot an arrow with the transformation, and it's going to be transformed. Okay, so and what we're doing is we are going to we are going this function sum. It takes as input a list of numbers, and it produces a number as the output. So we can think of a transformation as a robot, okay, that takes as input something and outputs something else. In this case, the robot sum takes a list of numbers as input and outputs a number as a result. And this number is precisely the sum of all numbers on the left. And there are...
And by the way, these two things that you can see here on this slide are very effective when we are talking about explaining this to young kids. Okay, so as we said before, the language of arrows, and then again we have also added this robot language, let's say, that in fact is very effective because they clearly understand how the transformation is being executed. Okay.
Yeah, and it gives a more fun aspect to it. You know, it's like, oh, little robot, little character. They sort of empathize.
Yeah. And most importantly, as you will see later, is that when you then combine those things again, the composition, okay, and you will have co-robots, okay, robots that dance with each other and by combining the transformations one after the other. Okay, so this is very effective in terms of from a pedagogical point of view.
Yeah, and there are several functions. When I say function or transformation, I will use as synonyms. There are several functions that take as input a list of numbers and output a number, namely, so the function sum returns the sum of all numbers in the list. Then we have a function called maximum that returns the greatest element in the list. And we have a function called length that returns the number of elements in the list. Okay? And now we are going to solve a very simple problem using some of these functions. So let's go back. I will share the other window. So now we will move on to activity 2. So Charles went to a restaurant, okay, and he ordered the hamburger, which cost €5. He ordered a large soda, which costs €2, a small coffee, which costs €1, and a chocolate brownie for €2. How much did he pay? So how are we going to solve a problem like this? So the point is you want to always solve a problem like this by applying a function to a list, okay? So we have here a list that models that represents the orders of Charles, okay? So the hamburger 5, then we have the soda 2, then a small coffee 1, the chocolate brownie 2. So this is the list that represents the data that we are given. And then we write this arrow here. So it's a vertical bar and then the greater than symbol.
Yeah,
and
no spaces between.
yeah,
Okay,
with
so-
no spaces between the symbols. And now we need to write which of these transformations allows us to do that. So if we want to compute how much Charles paid, what do we want to do to these numbers? We want to sum them, exactly, okay? So we write the instruction like this, and now we click play, and you should get 10. Did everybody get 10? Okay.
The importance of this is the following. Okay, so first you are modeling the problem, okay, because you are reading that story, real story, let's say, okay, that child went to a restaurant and so on, then that he paid those amounts to each one of the units or the ingredients that he bought, and then you are modeling that through a sequence of numbers, okay, through a list of numbers. And now, because you are modeling that as a list of numbers, you can apply that transformation, okay? So all this is computational thinking. You are modeling something, then you are applying a transformation on the model that you have specified, okay?
Can I just say something very,
Of course,
which is,
of course.
which is suppose after the brownie, if he feels sleepy and has another coffee, okay? And another coffee is yet another €1. And this is why repetition is important, because if it were a set, the two coffees would be would be one single element, okay? So that's why repetition in a list plays its role in computational thinking. Sorry.
No,
Yeah,
no,
absolutely.
great.
Good.
Yeah, and you can see there are two tools here. So the soda and the chocolate brownie.
Already, yeah,
cost.
all right. yeah,
Yeah.
yeah, right. Already,
Yeah.
okay. Yeah.
Yeah, thank you. So then we want to know how many products did he buy? So again, we will take this list of numbers because we chose this list to model the problem.
And
I'm
now,
just gonna
by the way,
copy
you
and
can
paste it.
you can copy and paste the result from
Okay.
cell. Okay.
And now we need to apply another transformation. So once we have this list of numbers, we want to know how many products did he buy. So what do we want to do to this list? we need to know how many elements it has, right? We need to know how many numbers the list has. So which of these transformations are we going to apply?
Yeah.
Length, exactly. So we want to know the length of the list, that is the number of elements the list has. And please write length this way, because it's a tricky word, and if you
Yeah.
don't write it correctly,
Yeah,
the
but,
computer
but you
won't.
can try to write it incorrectly if you want. Okay.
Yeah, say if you write linked, you will say, no, I don't know what that is. Perhaps you meant length. And yes, I did mean that. Thank you very much. So you should get 4. Everybody got 4? Good. And to finish, we want to know the price of the most expensive item. So what should I write? Yeah, so again, we are going to take our sequence and we are going to ask what's the maximum value that appears in this sequence. And I'm going to execute this cell and it's going to say 5 and it's correct. So the hamburger costing €5 was the most expensive item. Okay.
Another important thing here, for instance, of course, that this will be it's important to do all these things step by step, okay? But at the same time, by explaining each element that is appearing in our transformations and also mentioning in detail the kind of objects are we dealing with. Okay, so we are dealing with a list of numbers, but then the results, all these results are numbers. Okay, so in a sense, they are of the same type. Okay, so we are talking about results of the same type. Okay.
Yeah.
And this will be really important.
And then
yeah.
number.
Yeah.
And when you have a list, the list must be homogeneous in the sense that every element in the list must be of the same type. So if you have a number in the list, you must have only numbers in the list. And if you have a word in the list, you must have only words in the list. So if I tried to, when we wrote these first lists, I said, oh, the computer just accepted this, so it kind of told us the list back. But if I write like 1 and then I write, say, the letter A, which is not a number, okay, and I sort of execute a cell, is going to say, what are you doing? Okay, because if I start with a number, then everything else must be a number, and if I start with a word, everything else must be a word. We can't mix these types together. So it's very important to recognize the types of the data that we're dealing with.
And now a note only, for instance, to let you understand why, for instance, we are doing this in a very careful way when we are talking about going from this functional paradigm, for instance, to an object-oriented paradigm. Okay, is that, for instance, in an object-oriented paradigm, or even lots of programming languages, things like the one that Ines explained right now, is that, for instance, you may have a list of different objects. Why? Because the notion of a list is completely generalized. Okay, you are not talking about numbers, you are not talking about strings, you are talking about a more general object called object that can be anything. You know, the problem is that if you go to that level too early, then in our view, that will be bad for students to understand exactly what is going on. Okay, and that's why we are precisely working, for instance, with a language in the first place, with a language like Haskell, that it is very strict in terms of the objects that it deals with and the transformations that we can apply on those objects because they have specific characteristics. Okay, and that's precisely why in this language and at this moment it is not possible to create a list with different types of objects. Okay.
Yeah, and now you may be asking, okay, but like I could just look at the information and with my head just solve these problems. I could just sum this by hand, or I look here and I see 1, 2, 3, 4. Okay, it has four elements. So why bother doing all this? The problem is when you're dealing with lists that are huge and have big numbers. So if I ask you, okay, how many elements does this list have? You can answer, oh, it's 4. You don't need a computer to do that. But if you have this enormous list and I ask you, how many numbers does this list have? You don't know the answer. So we need a computer to do this. And so we are going to write something here. So what transformation should we apply to determine the number of elements on this list? Okay, so it's length. We want to know the length of this list, and it's indeed 200. And if we want to compute the sum of all these numbers, well, we just need to apply the transformation sum. Okay, and let's see. Okay, so it's 717,907. Okay.
That's right. Correct.
Wow.
Okay.
Very good. Cool. Now okay. So now I guess I will switch to the PowerPoint. Where are you? Okay, you're here. Okay, so we have already worked with lists of numbers that output numbers. Now we are going to look at functions that take as input a list and output a list. Okay, so functions that transform lists into lists. And we are going to work with these three functions. So function sort receives a list as input and returns a new list with the elements in ascending order. So from the smallest to the greatest one. Then we will also work with reverse. So it takes as input a list and returns a list with the elements in reverse order. So they appear like backwards. Okay. And then we have nub that returns a list with all the duplicates removed. So I may give you some examples before we solve the exercises. So what is the picture now? Well, before we had a list of numbers and it would give us a number. Now we have a list and it will give us a list too. So the input is a list, the output is a list too. For instance, robot sort writes the elements in ascending order. So here we have 4, 2, 3, 1, 2, 2, and he will write the numbers from the smallest one to the greatest one. So he will order the list like 1, 2, 2, 2, 3, 4. Okay. Wait, I need to.
Here is also important right now. Again, what I'm saying here between parentheses is related with specific things when we are dealing with these objects using a programming language. Okay, so as we were seeing there, we were just saying list, not list of numbers. That is saying that we may have lists of different types of the elements, and that transformation will work as well.
Yeah, we're going to see that.
Yeah, but not all the types. Okay, because in order, for instance, for us to order something, to put something in order, we need to have a way to compare the elements. Okay, but that's more stuff that it's not relevant here, but it's just for you also to understand exactly what is the math behind all this. Okay.
Yeah, so let me just give you some examples before we work this. So say I have 8, 1, 200, 1, 4, 3, 3, 1. I don't know, I don't care. Okay, so if I apply sort, it will order the elements, okay? So from the smallest to the greatest. Then if I apply reverse, what will happen is the following. So you see 8 was the first and now is the last. And 1 appeared second, now it's the last second one. And then we had 200, so 200 here. It basically just reverses the order of the element, so the list appears backwards. And finally, we have nub. Let's see what happened. So you see, nub is like, okay, I have an 8. Does 8 already appear in my list? No, it's the first time, so I'm going to include it. Okay, now I have 1. Does 1 appear already in my list? No, it's the first time, so I will include it. 200, does 200 already appear in the list? No, it's the first time, so I'm going to include it. 1, does 1 already appear in the list? Yes, it already appeared in the list, so I'm not going to write it. 4 is a new number, so I write it. 3 is a new number, so I write it. What about this 3? No, this 3 is a repetition because a 3 already appeared, so I'm not going to write it. And this one is also a repetition because I already have 2 ones, so I'm not going to write it. Okay, so basically it returns a new list with the duplicates removed. Once a number appears more than once, you ignore those occurrences. Okay. And now we will use these transformations to help Charles at the restaurant. Okay, so recall the list with the prices of the products, the hamburger, the soda, the coffee, and the brownie. And we want to sort the prices in ascending order. So what should I write? I will write first the object that I want to transform, which is this list with the numbers. And I want to sort the prices in ascending order. So what function should I use? Sort, exactly. So I will apply sort, and the result is going to be 1, 2, 2, 5. Okay, it ordered the elements in ascending order. And now what do I have to do if I want to reverse the order of the prices in that list? I will just use reverse. Okay, and it will appear backwards. And finally, actually, Charles was very lucky because on that day, the restaurant had a special offer. They said, if you buy 2 products with the same price, you only pay for one of them. So what is the list with the prices of the items that Charles actually paid for? Which transformation must we apply to this list in order to get the list with the prices that Charles actually paid for, given that if 2 elements have the same price, you only pay for one of them? So which of these transformations will help us do that? Not exactly, because we want to remove duplicates. So you pay for something once, with a certain value once, you don't pay for that again, okay? So he basically got a brownie for free because he had already bought something that cost 2 euros. And again, you might say, oh, those problems are so simple, I can do that without a computer. Okay, now suppose we want to sort this in ascending order. What should we do? Sort, exactly. See, all pretty 55, 88, 130, da, da, da. And you can clearly see. So if I asked you what's the smallest number that appears on this list, you wouldn't know. And if I asked you what's the greatest number that appears on this list, you also wouldn't know. But now if we have everything ordered, you can see that the smallest one was 55 and the greatest one was this one. I'm not gonna try to read this again. Okay, I will just to practice my number reading. 1,351,367. Okay, so now we are going now we are going to do more complicated stuff using function composition. So what is function composition? If you remember, when we talked about cryptography, we talked about applying a cipher and then applying another cipher, okay? So we were basically applying a transformation after another, and that's what function composition is about. So instead of applying just one transformation, we apply one transformation, and then we apply another transformation, okay? So suppose that we want to compute the sum of all the distinct numbers in this list, okay? So we don't want the sum of all the numbers. We just want the sum of all the distinct numbers. What should we do? So first, we need to remove duplicates. And how do we remove duplicates? So we go to this. So if you want to compute the sum of all distinct numbers, first we need to, remove duplicates from this list because we just want distinct numbers. And for that, we apply the transformation nub. And then we need to sum the results, okay? So first we take this list, we get rid of repeated elements, okay? We remove duplicates using nub, and then we apply the transformation sum to obtain the final result. Oh,
Okay.
success.
Yeah.
So rule number 1, if you have a problem with your computer, just restart everything and it will fix it. No, but that's the first step. That's the first step.
Understand what's happening.
Yeah,
Sorry.
that's right.
okay.
That's right. That's right.
So you see, we wanted to compute the sum of all distinct numbers in this list. So what do? We need two robots, okay? So first we have our list, and we need robot nub to remove the duplicates because we just want to sum the numbers that are different. So the robot nub will do that, and we will get the list 32714 after we apply nub. And then nub is gonna call his other friend robot sum, and sum is going to receive the output of nub and is going to produce the number 17, which is the sum of this list, which is the sum of the distinct elements in this list. So if we compose these two transformations, we go from a list of numbers, namely 3271724, to a single number, namely 17. Okay? So here. But not all functions can be glued together. So not all robots can take other robots' inputs. For example, say you want to apply sum after you apply maximum. That doesn't make sense because maximum produces a number as the output, okay? So maximum receives a list and is going to output a number. But then if you want to apply sum, you need to have sum needs to receive a list of numbers in order to sum the list and produce a number. So like if I am maximum and he is sum, I'm going to output a number and he's going to take the number and he won't know what to do with this because robot sum only works with lists, not with numbers. So we can't compose sum and maximum because they are not compatible. You see, here we need to have the same type and we have different types. We have number here and we have list of numbers here. And the number is not a list of numbers, okay? Great. So let's put this into practice.
Again, when we are talking about computational thinking, okay, so which is as you all know, no, it's very popular nowadays to talk about computational thinking.
That's
But
important.
this is precisely what's the importance of knowing exactly what's going on, what are we dealing with, in order to think in a computational way. Okay, so again, we are working with models and then we are applying transformations with specific rules that will put things working together. Okay, by doing these kind of exercises with the students, they will, from the very early ages, okay, they will start thinking differently when they are then dealing with problems, with specific problems that they will then try to model in somehow, and then they will apply transformations to that model in order to obtain results. Okay, this is not easy, and this is not something that will happen from the one day to the other. Okay, this need practices. Okay, but then after a while, we can see, and we are already also sharing with you our experience. We can see that yes, the kids start thinking in this way, and then of course after at the end they will have tools in order to solve problems. Okay, and that's the main goal of all this. Okay,
And I just have some minor comment, which is
Yeah, please.
different problems in reality can have the same model. That's why programs are generic and powerful. For instance, you gave this example of nubbing the sequence of numbers and then sorting it. Okay. In the music context that I mentioned before, music is a sequence of notes. So if I nub the sequence, I remove all repeated notes. And if I order them, I get the scale, okay? The scale in which the music is written, C major or whatever. So you see that exactly the same sequence of transformations is exactly the same, and the model solves more than one problem. It depends on the context. It's just this. Yeah.
Thank you. That's a very interesting example, and it really shows that computing can help us solve problems in many different fields, namely music. So these things are really useful and can be applied in several contexts. So here is the example that we worked here. Okay, here are all our robots holding hands. Now, look what happens. So I'm going to do a stupid thing. I'm going to say, okay, I want you to tell me what the maximum number in this list is, and then I want you to sort that. It doesn't make sense because sort takes as input a list, and maximum gives a number as output. So, okay, the maximum of this list is 5. And then I'm going to ask you to sort 5. You can't order a number, like that doesn't make sense. So it also doesn't make sense to compose functions that can't be glued together. Okay, so now this activity is a little more challenging. We're going to work with all 6 of the transformations we have learned so far. So to recall, the first 3 output a number. So we have sum, maximum, and length that output a number, whereas the last 3 output a list: sort, reverse, and nub. So let's look at this list. How many distinct elements does this list have? So we need to compose two transformations. Who can tell me what we must do to compute the number of distinct elements in this list? So what transformation should I apply first? Okay, I already heard a very shy nub. Okay, because we just want the distinct elements. So we want to get rid of all repetitions. Okay, and now that we have all the distinct elements, what do we want to do? So we want to know how many. So that's length, exactly, because length, okay, returns the number of elements. So I use nub to remove repetitions, and then I count how many elements does that resulting sequence have. And it says 195. So originally it had 200, but some of those are repeated, so the number of distinct elements is 195. And what if I want the sum?
And by the way, one important thing also, again, now we must think like a young kid, okay? So the importance of the order of the transformations, okay? So when they are reading exactly what we are asking for, okay, they start thinking not only in the transformations, but on the order of the transformations, which is absolutely relevant for this case, because if you put length before nub, okay, that does not work.
Yeah, so if I reverse the order, so I length and then nub, it won't work. It won't work because it doesn't make sense. I'm just, this is like asking the computer, okay, so how many elements does the list have? And it's gonna say 200. And then I'm gonna say, okay, so remove the duplicates from 200. That doesn't make sense because 200 isn't a list. But so it doesn't make sense when you say it, it won't make sense when you write it.
Yeah, but once again, we'll say, so we need to think and we need to realize that this is not easy for kids to understand, okay? And because they already have, for instance, in the first place, they already have the transformation in their head, okay? But then one thing is to have the transformation in their head, and the other thing is how to combine them in order to produce the result, okay?
Okay, and what if we want the sum of all the distinct elements? What should I write? So the first one is up, and the second one is sum. Exactly. So we remove duplicates and then we sum it all. And you can see it's slightly less than the number we got above. I don't know where it was. Here. 86717, and this one is 837.
Yeah.
Okay, so it's definitely okay. Okay, now this is a little more interesting. So I want to sort the elements in descending order. So function sort writes the elements in ascending order, starting with the smallest one and ending with the greatest one, okay? But now I want in descending order. I want to start with the greatest one and end up with the smallest one. So what should I do? Descending order, okay? I'm going to show you what you have in your toolkit. Exactly, okay, perfect. So if we sort the elements on this list, okay, and I can sort of see what we get, okay, it will be in increasing order, okay? So you start with the smallest one and you end up with the biggest one. So if I want the descending order, I need to reverse the order of the elements, right? So I need to write this list backwards. And now, Chana, we have it in descending order, okay? Very well. Great. Okay, so far we've been dealing with lists of numbers, because numbers, we are familiar with numbers, and we are also familiar with other stuff. So if I want to write a character on a computer, which can be a letter, a symbol, for instance, or something, I need to use this symbol, which is the, I don't know how this is called.
Is the quote.
Quote, yeah, but with a single, yeah, so single quote, so yeah, single quote, okay, to begin and to end, for the computer to understand that I want the type of the object that I'm working with is a character and not some generic thing. So if I execute this cell, it's going to say, okay, I accept the character A, I have received that information. But if I just write A and nothing else and hit the play button, is like, I don't know what that is. Okay, so we need to write the quote before and after the letter or the symbol or whatever. Otherwise, you will think that you are writing some name, but you're not assigning it to anything, so it doesn't know what you want to say. Okay, so when we want to represent characters on the computer, another data type, you need to write it on with quotes. And then between quotes, yeah. And then we also have strings. Okay, so what is a string? A string is just a list of characters. And strings are used to write words or sentences. So if you just want a single character, you use one quote. But if you want a full word or a full sentence, you use two quotes, double quotes. Yeah, I don't know the exact name, but yeah, so it's like banana, or I want $1 million now. Okay, so you write this double quote instead of a single quote. And this is also a list, okay? It doesn't look like a list, but it is a list. And why? So, for example, the list of characters HELLO space, okay? So the character space is single quote space, single quote, okay? This is the character space. So you're the space, and then if I have WORLD and then exclamation point, this list of characters is the same thing as the string hello world, because a string is just a list of characters, and you can confirm this by executing this cell. So here I have a list of characters where I can see, I look here and I see that it is a list because it starts with a bracket, it ends with a bracket, and it has commas, and all elements are characters. And if you hit the play button, it's going to convert it to a string. Okay, because like it's easier to read. This would be a bit confusing, so this is much easier to read and to write. It's much simpler. Instead of writing lists of characters, we can just write strings. And as we said in the beginning, we can apply some of the previous functions to strings. Okay, what functions can we apply to strings? Well, precisely these functions: sort, reverse, and nub, and length, and maximum. Actually, we just can't do sum, because sum only works with numbers, and we can sum letters. Like I say, what is A plus B? I don't know. It doesn't make sense. Okay. So we are going to apply now some of these functions to strings. So these are functions that that work with numbers, but can also work with characters. Okay. So I don't know if you are aware of this, but the longest word in the English dictionary is pneumo. Okay, I'll do it. Pneumonoultramicroscopic silicovolcanoconiosis. Okay, wow. Which is some sort of disease when you inhale ash and it goes to your lungs, something like that. Okay, so if we want to know how many letters this word has, we need to know the number of characters in the list that it represents. Okay, so what function should I apply if I want to count the number of letters? Length, exactly. Okay, so length gives the number of elements in a list, and the string is just a list of characters. So we just need to count the characters, and Chana, I have the answer, 45. So the longest word in the English dictionary is 45 letters long. And now, if we write these words backwards, what do we get? So what transformation should I apply to this monstrous word for it to appear backwards? Reverse, exactly, okay? And I'm definitely not gonna try to read. Oh, I will because it's fun. Cisardoconac, clovo, silis, hipoc, sor, simart, luonomuent. Okay, so that's the reverse of pneumo-ultramicroscopical silicovolcanoconiosis. And now, if we want to order the letters of this word alphabetically, what word do we get? So what transformation should I apply to order the letters alphabetically? Exactly. Okay.
Okay, but again, so here, why is this working? Just because we have an order when we are talking about letters, which is the alphabet, okay, the order in the alphabet. Okay, so since we have an order behind it, that's why sort works also on letters. Okay.
Exactly. Now, if we eliminate repeated letters, what word do we get? Nub. Exactly. That's simple. Pneumotrix. Okay. And if I want to know the length of this word, okay, so just, oh, that's the next exercise. I didn't see it. Okay, so how many letters does this word with no repeated letters have? So I do nub, so I eliminate repetitions, and then I'm going to do what? No, we want to count. Exactly. Yeah, we want to count. So it's length. Exactly. So this is only 14 letters long. Okay. If I want to know what is the sort of greatest letter that appears in this word, then I would use maximum. So it's going to say it's letter V, okay? Because it's like the greatest word in the alphabetic order. But if I ask the computer to, for instance, sum this, it is going to give an error because doesn't make sense. Okay, this is not a list of numbers; it's a list of characters. Okay, so this is the end of part one.
And again, let's have some time if you have questions.
Yeah, I'm going to.
If not, we'll ask you if you want to take a break or if we should go into the second part, which will deal with algorithms.
Okay, so yeah, questions.
So, but understood. So, as you can see, so after having this small number of things in your head, this is really powerful. Okay? Because as Professor Zanun was saying, so we have two things here. First, the same model can be applied and solve lots of different problems. One thing. Then, by knowing exactly how to combine transformations, And by the way, you can combine lots of them and put all of them in sequence, okay? And so you transform and transform and transform things, okay? And these quickly become very, very powerful and powerful tool to solve different kind of problem.
Yeah, Professor Zenon, I don't know if you want to add something.
I would add the following comment, which has to do with my experience in teaching at university. Students hate to reuse things. When you give them a problem, they want to write it from scratch, from nothing, and they invent the whole solution. And of course, this is very bad. This is very expensive. If they adopt that practice in a company, that's going to be very expensive because they are reinventing the wheel all the time. Why is this so? Because they have been trained like that. So this training from a very early stage invites them to reuse things, programs that have been already developed. These 6 programs, they are programs, they're going to see how to program them. So this idea that you solve a problem cheaply by dividing it into its parts, its ingredients, and then searching for programs that already solve those parts of the problem. This is very important. It doesn't look like important, but starting from this is very, very important because they go to a glossary or a repertoire or vocabulary, whatever, of functions, of operations, or transformations that are already available and pick the ones that together are going to solve the problem they have in hand. So I regard this as a very important ingredient because you have to fight when you teach programming against this tendency to do everything. I want to do it myself in my way, and that's of course very bad. Sorry, it was a bit
No,
longer
don't apologize.
a
You
bit
are
longer
very
than I
welcome.
thought. Okay.
Your comments are always welcome, and you always have something relevant to say.
Yeah, and if you can also see, so if you remember the 6 topics, around 6 topics that identifies what is computational thinking, okay? So you have already lots of them here, okay? Problem decomposition, abstraction, okay? So pattern recognition, because when you are talking about same model being applied to different problems, we are talking about pattern recognition. So once again, we are trying to discipline our minds in order for us then to have the tools to think computationally in a computational way in order to solve problems, and that's precisely what is computational thinking. Okay.
Okay, so if you have no more questions, I would say we take a little break and we continue to part 5 in a bit.
Yeah, 5 minutes or so.
Okay, so we'll 3 p.m. 2 p.m. in Portugal. 3 p.m. in Portugal, 4 p.m. here. Okay, so I'm just going to write that in the chat and see you in a few minutes. Okay, so welcome back. We will resume the hands-on session. And this part is going to be a little more, it's a little trickier, okay? It's mental, it's more complex, it's more general and abstract, I would say. We are going to talk about algorithms, but please bear with us and try to understand because it's gonna be worth it. So I am going to share.
Yeah, you have now a second link, okay, in the binder.
Okay, so we are going to talk about algorithms, and in particular, we are going to talk about a strategy called divide and conquer that Professor Zenuno mentioned in the beginning. And the naive idea of an algorithm is just something that you follow step by step, like a recipe to bake a cake or something. But rigorously and mathematically, an algorithm is much more than that. And we need a way, a formal way to write algorithms and to check that they are working correctly. Okay, it's not just, oh, I think this will work and I'm going to test it and debug it if necessary. Okay, no, we need a, a feasible way to construct algorithms that we can say are correct and work and do what we want them to do. Okay, so we have already used some functions over lists like sum, nub, and sort, but who programmed those functions? Okay, so somebody had to program those functions. They just didn't appear out of the blue. And so, for example, how can we teach the computer to sum a list of numbers without using sum? Okay, so what's the algorithm, or what a way that we can write this algorithm? So we can think of a computer as a very limited friend who knows almost nothing. Okay, so we need to explain clearly and rigorously everything we want him to do, because if we miss something or we forget a comma or a bracket, you won't understand this. Okay, and we also need to structure our train of thought very well, in order for everything to work correctly. And this is what algorithms are for. This is a very popular word that I explained intuitively, but now we are actually going to write algorithms and talk about the divide and conquer strategy, which is a really powerful strategy to write algorithms and to solve problems. So this is the first problem that we are going to face. We have lots of numbers, say 1,000,000 numbers, and we want to add all these numbers. You know, you can just apply the transformation sum, but suppose for a moment that sum doesn't exist, and you will have to write a function to do that. You will have to teach the computer how to sum a list of numbers. And we want to do this in an efficient way. Okay, we want to do this efficiently, meaning that we don't want to wait 5 years to get an answer. So we need to think very carefully what we want to do. And I'm going to show you a video that illustrates the strategy the computer uses to compute the sum of a list of numbers. And it can be illustrated through a binary help tree. Okay, so it's a binary tree that will help us. My cursor disappeared.
No. But okay, I will admit it. Anna.
Whatever. No, because it's like the cursor doesn't appear on my computer. It only appears on the screen. But it's okay. I can deal with it.
No.
Okay, so pay attention to this video. I will play it and pause it as necessary. Okay, so the input is going to be this list. Okay? And then we are going to successively divide this list into two, okay, one time and then again, until we get lists with only one element. And then we compute the sum of the lists with only one number, which are the ones on the bottom, and that's very easy, it's just a number. And then we compute the sums of the other ones by adding the results that we have below. Okay, so we have 1 and 5 there, and we get 6. And now for the other one, we add 6 and 7, and we get 13. And that is going to be the output. Okay, so what is the idea? I start with a list with 4 numbers, okay, which is like an easy problem, but let's pretend it's a million. So you're not seeing 4 numbers there. You're seeing 1 million numbers. So suppose you have a million numbers here, and we are going to split this list into 2 parts. So part 1, which is like the first half, which is 1, 5, and then we have part 2, which is the second half, which is 3, 4. And then we are going to do that again because we want to reach a point where we have really simple lists. And lists with only one element are like super easy to work with. So if I want to sum all the elements in the list that has only one number, the answer is just that number. So I will calculate the sum of the list with only one number and I get the results. And then once I have these basic results, I'm going to combine them to solve the big problem. Okay, so I went down and now I'll go up. So I will sum 1 plus 5 here, and then here's going to be 3 plus 4. So 1 plus 5 is 6, 3 plus 4 is 7, and I can't forget the 1, 5, 3, 4. I don't care about them. Okay, and then I sum 6 and 7 and I get 13.
Yeah.
And even if we had a million numbers, we would do this. Yes.
Can you just go to see the sum? Okay. So an important thing here also to remind you again is what we have said until now. And don't forget that we are trying to teach computing and to teach all these, let's say, new things on top of knowledge that students already have. For instance, when we are looking at this diagram and all this stuff, okay, we may, for instance, start playing a little bit with our students, saying that, okay, so we are talking about the sum of a list of numbers. Okay, so what operation do you know that in somehow is related with this problem? Okay. And when they then think about the sum of two numbers or the adding of two numbers that they already know, okay, they will then see that we are trying to explore a structure, a pattern that they know. Okay, and so when we are dividing here this again, okay, we are dividing this in 2 parts, okay, but the sum, when we are talking about the sum and adding 2 numbers, they are talking about 2 numbers that can be added, okay, and so in a sense, well, everything that we will see here, or the most part of the things that we will see here, are they already know about, okay, and this is again, one of the things that we are always trying to do when we teach computing, okay, is to, okay, remember this, and remember this. And now let's put these pieces in somehow all together and try to obtain new results on top of them. Okay. That's precisely what we will do here. And that's precisely how we will solve this problem and how will we build this algorithm in particular.
Yeah, and notice that the operation of addition is a binary operation in the sense that it receives 2 numbers as input. So here we have a 6 and a 7. So the plus operation only works with 2 numbers at a time. If you want to add 3 numbers, you need 2 operations, okay, not 1. And this is an important reminder also. So what's the general idea of the divide and conquer strategy? So first, we teach the computer how to solve really basic and easy and obvious parts of the problem. In our case, how to sum all the numbers in a list which just has one number. And then we teach the computer to decompose a big problem into smaller problems until it reaches a point where the problems are so easy that he already knows how to do that, because in step one, we taught him to solve basic parts of the problem, okay? So teach him the basics, teach him to decompose into basics, and you already have a solution to your problem. This is a nice diagram where you see you have this big complex problem at the top, and then you are going to divide it into sub-problems. So here you only have like 2 sub-problems, okay? And these sub-problems are easy, so we can compute them directly, okay? And then after we do all this splitting, we are going to merge or combine the results of these sub-problems successively until we reach the bigger problem. So first we go down decomposing, okay, splitting, and then we go up merging and combining the results that we will obtain. So now we are going to write an algorithm called add. I'm gonna call it add instead of sum because sum already exists, and we are going to write our algorithm. And what's the simplest possible case? As we have seen, the simplest possible case is adding all numbers in a list with just one number. And for us, this is obvious, but how do we tell the computer that the sum of a list with a single number is that number? Well, we are going to write it like this. We are going to say, okay, computer, if you want to add a list with a single number that we are going to call A, then the result is going to be equal to that number, A. So here A is a parameter, is a variable, like X in mathematics, it can represent 1 or 2 or 3 or 4 or whatever number. It's general, okay? So here we are designating that number, which can be any number, by A, and we are saying, computer, if you have a list with a single number A, the result is going to be A. Okay, now what do we do next? So now that we've taught the computer how to add a list with a single number, what should we do next? Well, we can try to apply the same idea and teach him how to add a list with 2 numbers, okay? So instead of just one number A, say that you have 2 numbers, A and B. Then we can tell the computer, okay, computer, if you want to add numbers, a list, if you want to add all the numbers in a list with numbers A and B, then the result is going to be A plus B. Okay, so now with these 2 instructions, the computer knows how to add a list with a single number and how to add a list with 2 numbers. So what could we do next? Well, we could teach the computer to add a list with 3 numbers and say, if you have 3 numbers, A, B, and C, then the answer, the result, is going to be A plus B plus C. But we can't go on with this forever, okay? So if I have a list with 1,000,000 numbers, I don't know. I don't even know how I would represent those 1,000,000 numbers. We don't have like 1,000,000 letters, so it will be just boring and cumbersome, okay? So we need a strategy. It can't be done by brute force, and by writing case by case, we need to be smart, okay? So, yes.
So just add one thing. Okay, so now so this is a gigantic step because we are already talking now about pure abstraction. Okay, so we are talking about algebra. Okay, so we are talking, for instance, about something that in math kids learn when they go to the 7th grade. At least in Portugal, but I think that probably is the same thing here because we are talking about when they goes from, what in Portugal goes from the 2nd cycle to the 3rd cycle, which means that, for instance, in England, it was when they go from the primary to the secondary stage of learning. Okay, so is when our mind is ready to deal with abstraction. Okay, so but here we are trying to deal with these kind of problems, okay, a little bit early. And so this is also some experience that we are doing, okay, with our students in order to see if we can find a way to deal with these kind of problems earlier. Okay, so and again, what Inez had shared with us until now is a gigantic step once again, but that represent and use a variable, so a letter, that can and is precisely saying us that this can be any number. Okay, of course that we need to deal very carefully with this when we are talking about students. Okay, most of the times we are doing these kind of things with kids that are already with 9-10 years old. Okay, but again, we are trying also to do experiments with early ages in order to see if this can in somehow be also explored earlier. Okay. So sorry. Just, oh, okay.
But yeah, we experimented this approach with variables and all with kids like 10 with 10-year-olds.
Yeah.
But we felt that it's a little early.
Yeah, it's early.
Yeah, it's a little early.
Yeah.
And we think it's better to do this only like 7th grade when there are like 13, 12, 13, because like there's this mental gap. So let me just show you something. Okay, so say that I start writing my program, add my algorithm, and I will say, okay, so if I want to add a list with just one number, then the result is going to be that number, okay? And so that corresponds to me saying the computer, okay, so this, okay, so add the list with one number and you get that number. And
Okay, estava trabalhando 4.
sim, estou
Okay,
só.
okay.
And let's see if it works. So what answer should he give me if I ask him to add the list with number 3? What should be the answer? What do we expect?
Yeah. Precisely.
It's just 3. And by the way, I can either write it like this or the way that we are more used to, okay? So I can write it like this. So computer, please add all the numbers in the list consisting of number 3. And he's going to tell me that it's 3, okay, because I told him, okay, if you have a number A here, hey is taking the value 3, so the result is going to be 3. And if I do that with any other number, say this, and I ask him to add all the numbers in this list, is going to tell me it's this number because I only have one number. And if I just give this instruction, the computer won't magically know how to sum a list with 2 numbers. So say I have 3 and 4, and I ask him to add, we would expect an answer of 7, but he doesn't know because I only told him so far here, I only told him how to add a list with a single number. So if I want him to be able to do this, I would have to say, okay, if you want to add a list with 2 numbers, A and B, then the result is A plus B. Okay, this kind of makes sense. And I execute this, and if I ask now, okay, so 3 and 4 add, now he knows because I told him. Okay, but again, it doesn't. If I ask him 3, 4, and 5, he won't know. He won't guess. Okay, I need to tell him that if I have 3 numbers A, B, and C, then the answer must be A plus B plus C. Okay, and now I ask him again, and now he's going to know because I told him. But we can't go on like this forever. Okay, we need a strategy, and that's what we are going to talk about. Okay, so back to the PowerPoint.
So we are, in other words, we are dealing with the basic patterns and then try to figure out what can be the general pattern that we can apply that is built on top of the basic patterns. That's precisely what we are trying to do here.
Yeah, and for you to understand intuitively this idea of divide and conquer, say that I have say that I have a big pile full of numbers or playing cards. Say that I have a bunch, like a million playing cards, and I want to sum all the numbers in the playing cards. And I say, okay, like aliens are going to invade the Earth and they are going to kill us all if we take more than 2 hours summing the cards. And we have 5 people here. What would we do? Okay, perhaps a million is too much, but say 100. So I could be narcissist or a tyranny
Yeah.
or whatever and say, you are going to sum all the 100 numbers. You are going to sum, Martina. That's bad, right? So what would be like a smart thing for us to do? Should only one person be working while the others are looking for stuff? No? Okay. So what could we do? Helper, and how can we help?
Yeah, an helper, yes, that's
So
right.
divide the task.
Yeah, let's divide the task, okay? So maybe I will sum 20 and you will sum other 20 and you will sum other 20 and you sum other 20, okay? So like, and we can all work at the same time, we work at the same time and each will sum this 20. And then we just need to add the values that we get to get the final result, okay?
And then there is a magic trick here. Because when we have the same problem, then we can repeat this process. Okay? Because we have started by having lots of cards, okay, and then sum all the numbers in the cards. Then we divide the problem. But we have the same problem. So we can do the same thing again.
Yeah, so actually the way this
Process, okay, the process.
because the computer deals well with the repetition and all of that, actually the way the computer would work would be more like this. So the alien comes to Earth and the alien has 100 cards with numbers for us to sum. And well, what we do is I may pick the cards from the alien and say, okay, Luis, I will sum 50 of them and you will sum the other 50. But you'll be like, that's still too much work for only 2 people.
Yeah.
So perhaps I'll think, okay, so I'm going to give 25 to Marta or Laura, and I'm going to give 25 to Laura.
Yeah.
And you may stay with 25 and give 25 to Martina. So we are going to just, and if there were more people, so we could say, okay, I'm going to give you these 2 guys, I'm going to give here. So we can all keep splitting into 2 until we get the
But
basic
again,
case.
what's important here for this mental process is to have already the capability of identifying a pattern. Okay, so the trick here is, it seems very simple, but again, it's a kind of we need to have our minds, okay, already in the right place to think like this. Okay, okay, so I have a pile of cards here with numbers, then Inez and myself, we look at what we have. And, wow, we have a pile of cards here as well. And then I give some cards to Martina, I give some cards, and you will look at what you have and wow, a pile of cards again, okay? And this is the magic trick. Because if you are dealing with the same problem, then we can now do some magic and we will be dealing with the same problem, all of us. So let's solve, and then at the end we will have the solution, and that's the magic part, okay? Because we are really dealing here with pure abstraction, as I told you, okay?
Yeah, so to recap, what's the overall strategy? So if the list has a single number, we tell directly to the computer, hey, little friend computer, if the list has a single number A, the result is A. And that's the basic case. All right. Now, if the list has two or more numbers, because we can't write, okay, A plus B, and then A plus B plus C, and then A plus B plus C plus D forever, what we are going to do is we are going to split it into two smaller lists and add the sum of them both, okay? And this is like the key, the important part, the most important part of our algorithm. So now I'm going to move on to the programming environment in order for you to see this in action. And this is like the most important part, and it's really, you need to pay attention because it's tricky.
And the good thing here, just a small note, is that, so now sharing with you again our experience. Yes, this is possible and to do with small kids. Why? Because they really play with this process very easily. The process. What is difficult for them, and that's why we need to do this in a later stage, is to write things. So the expression that Inez showed you 1 minute ago, that's the difficult part. Okay. But they deal with it like a game. Okay, they are playing a game, and they okay, blah, 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 and very easily they understand the mental model of the process. Okay, but not the writing. And that's precisely why we are trying also to do more things with the writing, okay? So once again, the SMS like thing of ways of doing things in order to see if in somehow we may in fact introduce this in earlier stages. But once again, it's an experience. That's why we are in a pilot, doing this in a pilot.
Yeah, and one thing that helps, but again, it's very tricky, is you thinking that the program already exists. Let me give you an example. So say I want to add all the numbers in this list. Add 3, 2, 5, 6, 1, 9. Okay, so I want to do this. And if I split the list into two parts, okay, so the first part will be 3, 2, 5, and the second part is going to be 6, 1, 9. So if my add program already existed, what would I write here and here and here? If it already existed, I could say add this. Okay, it's like I have a pile of 6 cards and I give 3 of them to Luis. Okay, so 3, 2, 5, and I give 3 of them to Laura, 6, 1, 9, and so they both add their cards, and then what I will do is I will sum the results. Okay, so like this is the idea if the program already existed, but it doesn't exist yet. However, this is like the basic idea. So I'm going to keep this as a comment. This doesn't work. It doesn't make sense. Okay, but how are we going to do this in the general case? So we have a function called split. And again, I can, oh, sorry, I forgot the first one.
And you can also execute this on your binder as well, okay? Don't forget to execute the first cell as Inez has just.
Okay, so again, I can write it like this, split the list, or I could write it like this, split, okay? It's like the same thing. Sometimes it's easier to write it one way, other times another, so I'm going to keep the original one, okay? And what is going to give me is going to give me a pair of numbers, okay? A pair of lists, a pair of lists. The first element of the pair is the list 3 to 5, which is, as we are going to see, part 1 of the list. And the second element of the list is 619, which we are going to see is the second part of the list. So then from this split function, we are going to have another two functions, so part 1 and part 2. And if I ask the computer, what is the part 1 of this list, what do you think the answer will be? Exactly. It's going to tell me it's the list 3 to 5. So it takes a list as input and it gives us the first half of the list. And if I ask what is part 2, okay, it's going to say 619. Now you can say, oh, but what if I add a list with an even number of with an odd number of elements? So say I have 3 to 5, 6, 1. Yeah, 3 to 5, 6, 1, whatever. So in this case, it's kind of there's no middle, but it's like, okay, so because we can't have 2.5 elements on one side and 2.5 elements on another, we are going to say that we have 2 here and then 3 here. Okay, so when you can't have exactly half the elements on each side, you do like more or less. One of the lists will have one element less, but that's not relevant. So what would be the part 1 of this list? Yeah, exactly. So part 1 of this list would be 3, 2. And part 2 will be 5, 6, 1. Okay? So I guess you already understand this part 1 and part 2. Okay, so here is our algorithm. Okay, this is okay. I am going to just because I don't want you to look at the rest yet. So how does this work? Can anybody understand what is happening here? Can anybody translate into English what is happening here? So remember the first example that I showed you. So what is the idea? So if I had the list 3, 2, 5, 6, 1, 9, then I would split it into a part 1 and part 2, and then I would add part 1, add part 2, and then sum the results. So in general, because I want my computer to be able to deal with any list and not just some specific lists, I'm just going to generalize and say, okay, so if I have any list, no matter the size, then I'm going to divide it into part 1, okay, and into part 2. And then I'm going to add part 1, I'm going to add part 2, and we sum the results. Okay, so
For instance, one exercise that we do, once again, when we are trying to check if this is possible to be explored in early ages, is precisely asking our students to explain orally what's going on here, okay? And they need to be rigorous when they are talking about what they are seeing there, okay? So, okay, the transformation head or function head, when applied to a list with a single element, the result will be that element.
Yeah, that's the first line.
And the second one, okay, so when we apply add to a list that is not a list of single elements, because that's already solved, but any other list, what will we do? Okay. And then, of course, that's precisely what we have on the expression there. Okay, so if we have the first part that is the same problem, and if we have a second part that is the same problem, then we have the head that is can be applied to these two parts. And at the end, what we have. And now an important thing in order to close this is once again the language of errors. Okay, because if in the beginning, when we are exploring and explaining the problem, when we say to them that, look, we will now build an algorithm that we'll call F, that will take a list of numbers and will produce a number. This is something that they get from the beginning. Okay, it's a kind of, you already are showing them part of the solution of the problem only by using the language of errors, by saying a list of numbers, an arrow that's called head, and here it will be produced a number. And so that's the last part that will close when they look at this and say, okay, now I will put the addition, okay, the addition of these two parts is because they are already looking at that head part one and that part two as the result that the head can produce, which is a number. Again, this is pure abstraction. Okay, this is not easy. It's really, really tough, in especially when we are talking about how at the age in which this can be done. But of course, that we already have some students that can solve this before the grade 7 and so on. But that's the solution for this problem. And again, this is a pattern that can be applied lots and lots of times to solve different kinds of algorithms.
Okay, so now we can sort of check if our program is working correctly. At least, I mean, this won't give us 100% certainty that it is working correctly. This will, but you know, if you add all numbers from 1 to 5, it's going to say it's 15. And if you sum these in your head, you will get 15. So yeah, that's all good. Now let's see if you can handle this list with 200 elements and doesn't take, no, it doesn't take long. See, it's very fast. It's like super fast. And he's constantly splitting until he gets to the base case and then adding them up. And he's like super fast doing that because it's a repetitive task. Split and merge.
We are talking about here as well an important concept. One of the most important concepts in computing is recursion. Okay, so we are repeating the same process again until the end, and the end is the basic problem that is already solved. Okay, so this is recursion. This is very powerful. Okay, and the basis of all the algorithms that can be executed in a computer. Okay, but again, what is behind the scene is precisely the, okay, in this case, okay, divide. Okay, it's a list with a single number. No, divide. It's a list of a single number. No, divide. At the end, you will have lists with single numbers, and so, and at that point, you will transform that into a number, and then you go up by summing, by adding these numbers, 2 by 2. Okay, 2 and 2 until the end. Okay.
right, so now we have some exercises to see if you understood these ideas. And the output of these following programs must be numbers, okay? So, yeah. The first one we want to build a program called prod to compute the product of all numbers in a numeric list. And here we are saying that if you want to multiply two numbers, we can use the star operator, okay? So like 2 times 3 is 2 stars 3, and it's going to be equal to 6. So, yeah. Okay, so what is the product of all numbers in a list that has a single number A? It's A, yeah, like there's nothing else to multiply by. So, yeah. And now, what are we going to do? And to help you, I'm going to write the add program. Okay, so the add program was like this. Add A, and then if we want to add any list with 2 or more numbers, we add part 1, and then we sum that with the addition of part 2. So what should I write here? Okay, imagine in your head that the program already exists and I have that list 615, I don't know, 319 or something. Okay, so if I split it into two lists, I will have the first one, I'll say part 1 is going to be 615, and then part 2 is going to be 319. Okay, so I have 6 cards, 615, 319, and I'm going to give 3 to Luis and 3 to Martina. And what will I ask them to do? My goal is I want to know the product of all these numbers. So what will I ask them to do? The product, yeah? Okay, so what's the product of your numbers? And what's the product of your numbers? So I'm going to ask both of them, what's the product? So prod of the thing, the card that you have in your hands. And then what will I do once I have the result of Luis and the result of Martina? What will I do to those numbers? I want to sum, but I want the final result to be the product. Okay? So I want the final answer to be 6 times 1 times 5 times 3 times 1 times 9. And Luis computed 6 times 1 times 5. Martina computed 3 times 1 times 9. So I have 6 times 10 times 10 times 10. So what do I need to do with this to get the product of all numbers?
I will not say to you.
Okay, so let's go step by step. So Luis answer 6. So Luis is going to tell me so 30.
30.
Okay,
yeah.
so it's like 6 times 1 times 5, which is equal to 30. And what is Martina's answer? Yeah, so she's going to tell me 3 times 1 times 9, which is 27. What must I do to 30 and 27 in order to have, so Inês,
The final product of this
yeah,
is 30.
exactly.
Yeah, then.
Okay, 30 times 27. So what should I write here? Is it plus? No, it's multiply, exactly.
Is the star.
Okay, okay, so now that we have this example here, okay, I need to, what will be the general case? So here we have this specific list, but what if I want any list? What should I write? And you just need to look at this and pretend this is list. And then if this is the list, then this is what? Exactly. So I'm going to ask products of part 1 of the list. Then I'm multiply by the product of part 2. Exactly. Okay. Now I can delete this. Okay, I can also leave it because it's when I write the two minus signs, it's like you will ignore this. Okay, now let's execute this cell. Okay, I already wrote the program here and I executed the cell, but it didn't tell me anything because I haven't written any list yet. So I'm going to ask him the product of all numbers between 1 and 5. And what should be the answer if this is correct? So 2 times 3 is 6. And 4 times 5 is 20. So 6 times 20 is 120. Okay? So I guess this is working. And we can test with this other example here. So if I had 6, 1, 5, 3, 1, 9, it says it's 180, okay, which is precisely 30 times 27. Okay.
What is important to notice here is that this is happening not by chance, okay? Because you can see that the pattern of this algorithm and the pattern of the F algorithm are exactly the same, okay? And why is that? Just because multiplication is related with the addition, okay? In fact, multiplication can be decomposed into a sequence of additions, right? Okay, so, and that's precisely why when we are talking about product and addition or sum and product and so on, we are in fact exploring the same structure when we are talking about the basic operations we are dealing with. Okay, the addition in one case and the multiplication in the other case. And that's why this, at the end of the day, because we are exploring these basic properties of the math, of these math operations, we are in fact having the same pattern when we are talking about the algorithm that is built on top of those structure elements.
Yeah, so instead of add, we are calling it prod. That's one difference. And then the other difference is that instead of plus, we are going to multiply because now we want a product and then we wanted the sum. Okay, that's the only difference because the rest is the same. The rest is the same. And so you may wonder, so what if we put here a plus, like Marta had suggested? Well, I don't know what it will say, but it won't be correct. So see here, if I put a plus here, it's going to do the sum, okay? Because you will be always summing. There's nothing here that tells him to multiply, okay? So if we want him to multiply, we need to use the multiplication.
We have changed the basic operation of the same pattern. Okay, the process is the same, yet changes only the basic operation, and we have the difference.
Okay, so now to end this part, we want to write the length program, okay, that we are going to call count to compute the number of elements in a list. Okay, so what we need to do, we need to tell him, so how many elements does a list with a single element have? So if I have a list with number 3, what should be the answer?
This is the number of elements in the list, 1. Exactly.
Yeah.
1. So we are now
one number.
Yeah, we are now writing the length. Okay, that operation that we have used before.
Okay, And now we have the other thing. So again, say that I have a pile of numbers and I give part 1 to Louise, I give part 2 to Martina, and Louise will say, okay, there are 13 numbers here. Martina will say there are 15 numbers here. What do I need to do to the results?
I have the number of elements of my parts. Martina, the number of elements of her part. Now I have these two numbers. What I need to do with them?
Yeah, you sum them, you know. So if he has 13 apples and Martina has 15 apples, then the total number of apples is 13 plus 15, which is 28.
Yeah. And so again,
So
you will look at the pattern here and will compare with the others.
yeah.
And again, you will see the small difference that is changing the result of the algorithm. Okay.
Okay, so here I want to count how many elements we have in the first part of the list, and then I want to add that to the length or the number of elements in part 2 of the list.
Okay.
And I'm going to execute this and see if it's correct. So yeah, that's the expected answer because it has 5 elements. Okay.
So the difference
Yeah, look at the difference between, I'm going to move these below.
Yeah.
So look at the difference between add and count. Where is the difference? Besides the name, I could call it the same name, whatever. But where really is the difference? Yeah.
The
So
basic pattern.
the second line is the same. The second line is the same. I'm just calling different names. But the first line, that's the difference. Because if we count the number of elements with a list with a single element, the answer is 1. But if we add all numbers in a list with a single element, the answer is not 1, it's that number. Okay? Yeah, it's the element. So that's the difference. Okay? So this small change in the program yields two completely different programs. All right. Now we want, do you remember those programs, for instance, reverse? Do you remember the reverse program, which writes a sequence backwards? What if we want to program reverse? And it's a bit of a complicated problem. So before that, we are going to deal with a simpler problem, but still complicated, I'm sorry. So let's switch to the PowerPoint.
And this is the final part. Okay. Because you're already tired.
Yeah, we are too. So say I want to write an algorithm that takes as input a numeric list and adds 1 to every element in the list. So if I have 1, 5, 3, 4, I'm going to add 1 to 1 and I'm going to get 2. Then I'm going to have 5 plus 1, which gives 6. Then 3 plus 1, which gives 4. And then 4 plus 1, which gives 5. How can we use the divide and conquer strategy to write such an algorithm? Now, what's the difference? What's the main difference between this program and the programs we have seen, like count and sum and length? Count, sum, and or count, add, and whatever.
Count, product
and
sum.
and count. Add, product,
and product.
Yeah. So what's the basic difference? The difference is that the output of this program is a list, whereas the output of the other programs was a number. Okay? So how can we use the divide and conquer strategy to write this algorithm? And we have a little video for you. So we have this list. Okay, this is our input. And as before, we are going to split it into two parts and split into parts again until we have only one element. Then we are going to add 1 to all numbers in the list with only one number. So it's going to do that. So it added 1 to a list with one number. And now what we're going to do is we are going to join the lists. So if we join 2 and 6, we get the list 2 plus plus. The plus plus is the join operator. Okay. And then we join and we get the end result. Okay. So let me.
So the plus plus together now, it's the joint two lists. Okay, we have a list here, here. We have a single list with the result of joining them.
So let's explore this plus plus thing. So you see, if I want to join the list 1, 2, 3 and the list 4, 5, 6, I write plus plus. So this is list concatenation. It's not a sum because you can't sum lists, but you can join the elements of the lists together. And it's gonna say it's 1, 2, 3, 4, 5, 6. Okay, so this is used to join the elements. So now let's look at the algorithm for add 1. So this, we want to add 1 to every number on the list. Well, if I have a list with only one number, the result is that number plus 1, right? So if I have a list with a single number a, the result is going to be the list with a plus 1. Because I want to add 1 to all elements in the list. So if it's 2, I want 3. And if it's 3, I want 4, and so on. And then what are we going to do? Well, we are going to take our list. We split it into part 1 and part 2. We add 1 to all elements in the first part. And then we add 1 to all elements in the second part. And we join these elements to get the final result, okay? So, for instance, if I want add 1 to 1, 2, 3, 4, 5, 6. This is going to be like, okay, so add 1 to every element in 1, 2, 3, and then join the result with the result of adding 1 to every element in the list for 5, 6. Do you agree? Okay, so the computer, this is like how the computer thinks, okay? So the computer, what we'll do is basically, okay, I have a list with 3 elements. That's still too much. So what it's going to do is going to split this one more time. So this is like the add 1 of the list with just 1, plus the add 1 of the list with 2, 3. Right? So this part is this. Do you agree? And then what else? What are you going to do with this part? Add 1, 4, exactly. And then plus add 1, 5, 6. Yeah. So this is too big. I need to reduce it a little. Okay, and now it still needs to do some work. So he already knows that add 1, 1 is what? So we already told him, right? So what is add 1 of the list with the number 1? He already knows it. We have told him that. So what is it? If I add 1 to 1, I get 2. Exactly. So this thing he already knows is the list with number 2. Now this is a list with 2 numbers. That's still too much. So he's going to split this list into add 1, 2 and add 1, 3, right? Okay, and now he knows this. So what is this? it has only one element, so 4 plus 1 is 5. So it's going to be list with just 5. And then we need to split this. So it's going to be add 1, 5, plus, add 1, 6. Now, is the computer in conditions to give us an answer? Well, this is already a list, and now he already knows this. Okay, 2 plus 1 is 3. And then he already knows this. 3 plus 1 is 4. And then he already knows this is 5. Oops, what am I doing? Okay, so 5. And then he already knows this. 6. And he already knows this. 7. Okay? So he will finally tell us, okay, the answer that you get is 2, 3, 4, 5, 6, 7. This is how the computer thinks, okay? This is not what we write. What we write is this, but internally, the computer is going to do all this process, you see? So he is going to do the splitting, and then he's going to do the merging, combining the results. Okay, so I can keep this here, whatever. Let's just check if this is correct. So it's correct. You see, it's working. So now the output of the following programs must be a list. Before it was a number, now it is a list. And the first task, and I'm going to copy this one for you to have some inspiration, is we want to write a program called doubles. Okay.
Well,
that doubles or multiplies by 2 every element in the list. Okay, now I'm going to, this was add 1. Okay, so for you to have some inspiration. Now, what is the result when I have a number A and I multiply it by 2? What do I get? What is the expression? So before I wanted to add 1, so I have A plus 1. Now I want to multiply it by 2, so what do? I multiply it by 2, right? So it's A times 2, right? Okay, and now what do? I know that I'm going to write, I'm going to duplicate every number in the first part, and I need to do something, and I'm going to duplicate every number in the second part. So again, say I have a list with 6 numbers and I want to duplicate them all, and I say, Luis, please double the first 3, Martina double the other 3. What do I do to get the full list? I need to join, right? So here I'm going to join the lists, okay? And that's it. So what's the difference between these two? Well, in this one, I wanted to add 1, so I wrote plus 1 in the base case. And this one, I want to multiply by 2, so I multiply by 2 in the first case. But the second line is exactly the same, because the idea is after I have both results, I join them. Okay, after I have both lists, I join them. So if, for instance, if I double every element in this list, I get 2, 4, 5, 8, and 10. And now I think we better finish with this one, because this one is a little tricky, but you can see. So we want to write a program called replace to replace every element in a list by the string hello. Okay, so again, our 2 lines, we have replace of a list with a single number and replace of a general list with 2 or more numbers. So if I want to replace every element in a list by the string hello, then A will be replaced by what? What should I write here inside these brackets? Hello, exactly. Hello. Okay. So it's like if the list has a single element, then replace that element with hello. And now I need, it's the same thing. So I split it into two parts and I need to do something. Okay. So what do I do?
Back to list.
Yeah, I need to join them, exactly. So I just need to join them because it's like I have a list. So 1, 2, 3, and 1, 2, 3, 4, 5, 6. And I will give Louise 1, 2, 3, and he's going to say hello, hello, hello. And I give to you 4, 5, 6, and you're going to say hello, hello, hello. So if I want 6 hellos, I join them together. So, for instance, the result would be this one. Okay? And I think that was already a lot for today. So there's still this exercise if you want to think at home, but it's a little trickier. It's basically to program the reverse. So think about it at home if you want. And if you have any question, please ask. And I don't know if Professor Zenon wants to.
And now, Martina, I will put the link here. So 2 things. Let me share my screen now.
Oh, yeah,
Just
course.
to,
Whatever. I will stop sharing. Yeah. But before that, does anyone have questions? So, Professor Zenon, I don't know if you want to say something.
Yes, this is more elaborate than what we had before, but there is something in between. Remember that which we haven't shown here, which is that idea of the help tree. Okay, so for younger kids. So this, I think we tried this with year 9, grade 9.
Yeah.
Have we tried before this?
No.
No.
I mean, perhaps 8th and 7th.
Yeah.
And in some workshops with the younger kids, but it's always difficult. Like they understand the idea, but writing the program is difficult. But the tree part and the idea of the algorithm they do understand, but writing it is a little more subtle.
Yes. And yeah. I'm going to put in the chat the reference to a paper by a colleague of a computer science colleague, which is very interesting. So if you want to have a look at how we, because he has studied this a lot. He's a very good professor, and he has studied this a lot in this connection to when do children are able to cope this idea of that A representing an arbitrary value. Okay,
Yeah,
it's not a single value.
tricky.
It represents any value. That's a big change. That's a big change, and I think he says that it's about around 12 years. I think 12.
Yeah. It's between the second and third cycle. Yeah.
So there is clearly a limit,
Yeah,
a lower
between-
bound on when we can actually teach this. It's exactly that spot line where they become capable of handling this abstract notion of a variable, because that's what it is. It's a variable. Yeah. So if you have time, have a look at that paper because it's quite interesting. He has done lots of experiments because he's a teacher of distributed systems. And the distributed systems and parallel systems are even more complex than the ones that we have here. And so he has worked a lot with these ideas. Okay, so that's it for me.
Thank you very much.
Thank you.
Yeah, okay, so now I will just share the screen in order to, okay, just to show you this. Okay, so in the Cisco platform, okay, so we have there, so we have there this blended mobility, and then we will have the links to the binder, Okay, so here, when you click on hands-on activity by part 4 and part 5, and then you have this questionnaire. And I will now share this link to the questionnaire also in the chat, okay, in order to. So all the people that want to, not only you that can then fill the questionnaire, but also all the people that can then see the videos and also do the exercises in the binder and then to answer the questionnaire in order for us to collect the responses and to get feedback on everything that we have done today.
Okay, so if there are no more questions, I think this is it. Oh, I already stopped for you.
Okay.
And thank you so much for everyone for your participation. You're at home.
And you need a rest because it was a long time.
Yeah.
It's rest.
Yeah,
yes.
very long. Yeah, very long.
Very long. Okay, good.
But so, Martin, I think that if you want then to say to all people that they have the entire week if they want to see the video. Okay, so the videos will put.
We can give them some time
Yeah.
to do the video. So
Yeah.
what we thought about this, people who are not connected today, we went to do. I would do follow up with them and see in the next few days. Send them the link when you
With videos and so on. Yeah.
Then I will send them the link and ask them, hey, would you like to go there and see the video?
Yeah.
And
Percent.
maybe we can give them time until the end of June.
Yeah. Perfect. Yeah.
We should like decide. We can discuss it tomorrow in the meeting. We should decide on a day when let's say the training closes, the last day when they can deliver their work.
Yeah.
Just to let them know and say, okay, so we offer you flexibility. If you couldn't assist the day we did hybrid learning, then you have the chance to review the material, the resources, do the activities. Share your feedback, and you have to, in order to have the certificate for this module, you are required to do this before fix a day. But the next day, we will check it and
It's fine. It's fine.
Generate the certificates for everybody.
Yeah. Because after the next webinar, they will have the first part of the series, okay, and then it's only the last one, okay, which is Python learning. Which is different from this. Yeah.
Still, they will have some work to do, and probably the workload for the Python will be higher than the workload and all the exercises.
Yeah. I think so.
So I think they will have to do quite a lot of activities for Python, which is not that required because they can review all of the video from today and go through the binder and see the exercises, and they can do it probably in a shorter time.
Yeah, sure.
Yeah. So I think this can stop and we can. So bye and thanks everybody.
Yeah. Bye and see you next time.
Bye.
Yeah.
See you next time.
Bye.
Não, obrigado mais uma vez.
Bye.